In this video, we're going to discuss linearization. What is that? Well, here in linearization, we're going to learn how to approximate complicated functions with linear functions. So let's assume we have this more complicated function here, f of x. And maybe we know some point a comma f of a on that function. And what we want to do is we might want to estimate f of x over here. So we have some x value and we want to estimate what the y value is at that particular x value. And so that's what I have written here. We want to estimate our value f of x. Well, how can we do that? Well, we can think about the equation of this tangent line. The equation of that tangent line is y is equal to f of a plus f prime of a times x minus a, right? If our point slope form says y minus y1 is equal to the slope m times x minus x1. And so a is x1, f of a is y1. And so this gives us the equation of our tangent line here. And now how are we going to use that? Well, we can notice that we have a triangle here, and this point up here is our value f of a plus f prime of a times x minus a. That's what this y value is up here. And notice that we're off by some amount from the true y value, but it's pretty close. When this x value is close to a, this value can approximate this value. And in fact, the closer we get to a, the better the approximation is. So that's exactly what we're going to do. The equation of the tangent line is here, and this tangent line approximates the curve f of x near a. So we call f of x equal to L of x, or sorry, f of x approximately equal to L of x, which is equal to f of a plus f prime of a times x minus a. We call this the linear approximation or sometimes the tangent line approximation, or sometimes just the linearization of f at a. The linearization. And again, what does this do? It gives us a linear approximation of our function. And this works when the x value we're trying to calculate, or the f of x value we're trying to calculate, has a corresponding x near the point a comma f of a. Right? So when this x is near our a comma f of a. All right. So let's go ahead and do an example of this. So example 1 is just going to be to find the linearization of the function f of x equal to the square root of x plus 3 at a equals 1, and use it to approximate the numbers square root of 3.98, and the square root of 4.05. So these are the values we want to approximate, but we first need to find the linearization. So again, the formula that we're going to be filling out is this one up here. So make sure you write that down. And then let's calculate that now. So first is we need to find out what f prime of x is. F prime of x is, here's our f of x, so that's x plus 3 raised to the 1/2. The derivative of that is 1/2 x plus 3 to the negative 1/2. Chain rule then says to multiply by the derivative of the inside. The derivative of the inside is just one of those, so we multiply by 1. So we're really done here, and we can rewrite this as 1 over 2 root x plus 3. So f prime of 1 just means plug 1 into here, so we get 1 plus 3 is 4. Square root of that is 2. 2 times 2 is 4, so this is 1 over 4. And we also notice that f of 1 is 2. So, putting all of that together, we see that L of x, our linearization, is equal to f of 1, which was 2, we'll get to that in a minute, plus f prime of 1 times x minus a, so it's x minus 1. So all of that is equal to 2 plus 1/4 times x minus 1. And if we distribute and then combine, we end up with x over 4 minus 7/4. Sorry, plus 7/4. Okay. And so this gives us, again, L of x is equal to x over 4 plus 7/4. Well, what we have said is that when x is near 1, the square root of x plus 3 is approximately this value, x over 4 plus 7/4. Or whatever near 1 means. Okay. So what does that mean? That means it can approximate these values. So what is the square root of 3.98? Well, it is approximately the square root, this is equal to 0.98 plus the square root of 0.98 plus 3, which is approximately, now we can use this, so this is x over 4 plus 7 over 4, where x is 0.98. And this is equal to 1.995. So our approximation of the square root of 3.8 is 1.995, according to our linear approximation here. Well, what is the actual result to this? If you plug that into your calculator, you see that this is approximately 1.99499937. So we see that we got ridiculously close here. In fact, tenths, hundreds, thousandths, 10,000, 100,000ths, right? Hundred thousandths. Yeah, we're off by like 6 1/millionths. A little more than 6 1/millionths from the correct answer. Which is a pretty good approximation. Especially for how quick this kind of an estimation was, how quick that calculation was. Let's go ahead and do the same thing for the square root of 4.05. Well, this is equal to 1.05 plus 3, the 4.05 is. So the square root of that is just equal to the square root of 1.05 plus 3, which tells us our linear approximation then is 1.05 over 4 plus 7/4, which is equal to 2.0125. The actual value of the square root of 4.05 is 2.01246111, or at least when rounded to this many decimal places it is. And again, we see how close that is. It's not quite as close. We're off by about 5 or so hundred thousandths. So it's not quite as close as our previous approximation. But also, the further away we get from x equals or a equals 1 here, then the further away our approximation will get. We're going to get less accurate results. So it kind of makes sense now that we're 5 100ths away, that we're a little further away on approximation compared to when we were 2 100ths away. All right. And so with this example, you can see the power of this idea of linearization. These calculations are much faster, much easier to do than the calculation of the square root of 3.98. How your calculator actually does that is through something called Taylor polynomials, which we'll learn about in Calculus 2. And that is easier than actually calculating a square root kind of calculation, but it's a little bit more difficult than this idea of linearization here. So again, we see how powerful that can be in this example. All right, and that's going to end this first video.